Water. So we're going to be talking about the things about water that are important for biology, or at least some of them. Life originated in water. Here's a picture of cells, and this is blood that's inside of a capillary, and this is the fluid that's between the cells and the blood. So all of your cells are immersed in water, and they have water inside of them. So you're made up of a lot of water, and all of your chemical reactions happen in water. So all metabolic reactions occur in water. Metabolic means all of the chemical reactions in your body. So these are building maybe proteins or building any molecule or breaking any molecule down. So every chemical reaction in your body is considered a metabolic reaction. And they all take place in water. You're mainly made out of water. So this is the way that reactants can come together because they bounce into each other because they're dissolved in this liquid. Here's again what water looks like. So if you remember from our last video, this side is the oxygen. It's got 8 protons, and so it's really, really positive. And so they attract lots of electrons. So the shared electrons between the two are much more attracted here. And instead of just having these 8 positives balanced off with 8 negatives, you have maybe 8.5 negatives, something like that. And so overall, this side is more negative. And these are just one puny little proton over here each. But instead of having one negative over here, maybe they have a little bit more, maybe more like maybe a little bit less, because the extra bit is up here. So maybe 0.75 or something, I don't know. 0.75. So this ends up being more positive. So what I want you to remember for water is that it's polar, meaning one side is more negative and one side's a bit more positive. Water is polar. I just said that. So that means an uneven charge distribution where one side is a bit negative and one side is a bit positive. Ions and polar substances dissolve in water. They are hydrophilic. Philic means to love in, I don't know, I want to say Latin, and hydro, of course, is water. So these things love water, or, well, they don't really love water, but they do dissolve in it. They don't stay away from it. When salt, which is sodium chloride, at least that's one type of salt, dissolves in water, the water molecules separate the salt into sodium and chloride ions. So I'm going to show you what that looks like. Here's a sodium ion, and that's not a partial positive charge, that's a full positive charge. So this ion is positively charged, and if you look at the water molecules, the negative side, the oxygen side, is the side that orients itself toward the sodium. And the reason that the sodium and the chloride separate is that the water squishes in between, and the water is very attracted to it. This water is more attracted to that than it is to the partial charge over here. And so they line up around sodium, and the opposite is true over here. The positive sides all line up around this negative chloride ion. And so they push their way in and separate out these two ions. And so that's why ions dissolve in water, because the water is more attracted to the ions than to each other. Because water is polar, large nonpolar substances are repelled by it. So what you're looking at here, these pink things are water. And what I want you to look at first is this picture over here. These things are all nonpolar, so let's say that's some type of fat. Maybe little fat globules or some kind of oil, whatever. And so there's nothing in here for water to be attracted to. It's not an ion, so there's no positive or negative charge, and it's not polar, so there's no partial charge. So this negative side of water is attracted to this positive side of water. It's not attracted to anything in here. So what will end up happening is the waters will all be attracted to each other and they'll come together. So this is the before, and over here is the after. The lipid will stay away from the water because the water is not attracted to it. So if you're this water molecule, you're going to be much more attracted to that end of another water molecule than to anything over here. So the moral of the story here is that polar things dissolve in water and nonpolar things are repelled by water. So if you've ever seen oil and water together and you shake them up, they'll mix for a little bit, but then they'll separate. So these nonpolar things, since they don't like water, it's not that they don't like it, but since they're repelled by it, they're called hydrophobic. And so you can remember that because a phobia means fear. So for example, arachnophobia is a fear of spiders. Agoraphobia means afraid to go out and to see other people, like afraid to go out of your house, for example. You can pick your favorite phobia, but it all means fear. So these things that are nonpolar, if they're nonpolar, we're also going to call them hydrophobic. Oil is an example of a nonpolar or a hydrophobic substance. So that's actually really important. The reason for me to go into this whole polar-nonpolar thing is so that you can understand what nonpolar things do with water and then what polar things do with water, because your cell membrane is set up because of all these things. So here's oil, and it's hydrophobic, and in here is water. And you've probably done this with salad dressing. You take the oil and the water or the vinegar and you shake them up and then they separate out. And that's what is happening here. The water and the lipid or the oil are separating out. If you've ever washed a plate that has lots of butter on it and you don't have suds yet, you'll see that the water just kind of rolls right off of the butter. It's the same idea. Quiz time. Oil is it going to be hydrophilic or hydrophobic? Well, oil and water don't mix, so phobic would be fear of. So it's that one. Polar, nonpolar. I'm actually way more concerned that you know these, but you might as well know these too. Polar means there's a different charge distribution. Remember, the poles of a magnet are different. You've got north and south. The poles of water are also different. You have a partial positive and a partial negative. So if oil doesn't like water, then it's going to be the opposite. It's going to be nonpolar. Sugar dissolves easily in water. So because of that, sugar must be, well, if it dissolves easily, it must like water. That's hydrophilic. And the only reason it would dissolve in water and like water is either if it's an ion or if it's just like water, which is polar. And the reason that sugar's like that, let's see, sugar might look something like this, and it's going to have some, I don't care if you know exactly what the structure looks like, but look at this. It'll have some OHs hanging off of them. And this looks a whole lot like water, and you'll have a bunch of them in other places too. Okay, our next segment is chemical reactions. I'm going to do that in a different segment. So, goodbye.